this recording, we're going to look at the validity conditions of the pH use for weak acids. And at the beginning, I'm going to look at the general case where we actually will not neglect the autoionization of water. And I'm going to show you that in that case, we get a third-degree equation. And to decrease our mathematics, and in order to not do a third-degree equation, then we assume that autoionization of water is negligible. And we actually will only calculate the pH of weak acids when the autoionization of water is negligible. In that sense, all the pH calculations of the weak acids, which we had already looked into, were the case when we were not looking at the effect or the contribution of water towards acidity. It was only the acid dissociation that we were looking at, which gives me a pH value. So I'm going to give you a general case first, and then we're going to look at the autoionization of water when it is negligible. And then if it is negligible, then there are three cases which we will look at. And we will look at if the acid weakly dissociates, or moderately dissociates, or greatly dissociates. If it weakly dissociates, it means that the percent ionization is less than 10%. In other words, alpha is less than 0.1. And if that is the case, then A- is negligible with respect to HA. And when we solved, that means that X is negligible. Remember that X, we neglected it on the bottom. So A- is negligible. And that is a condition when we will see that C is greater than 100 Ka. Then we will look at moderately dissociated acids, and those acids dissociate more than 10%, but less than 80%. I mean, this 80 or 90 or less than 99, I mean, it doesn't really matter what this number is. Different people take it differently. But the percent dissociation is greater than 10. If the percent dissociation or ionization is greater than 10, that means we cannot neglect the A-, or I cannot neglect X, and I have to do a quadratic equation. And we will see that that means that C is actually less than 100 Ka, okay? And there's this extra part, and that is another limitation, and that is when the acid greatly dissociates. And in a sense, that's when the percent ionization approaches 99%, or that this acid, it's a weak acid, but it's dissociating so much as if it's going to be a complete dissociation, thus acting like a strong acid. In that case, HA is negligible with respect to A-, and we will look at that sense. That means actually that it's acting as a strong acid. That means that the concentration of HA, there's nothing left over pretty much in solution. Most of it has been converted to A-. Let's start with the general case. So if I have a general case of a weak acid, okay, we have the equations first. So we have a weak acid dissociation with a Ka, and then we have the autoionization of water dissociating with a Kw. If we look at the species, actually, if you just look at the equations here, all the species are present. We have water, we have H3O+, OH-, all from everywhere. The OH- is only coming from the water dissociation, and the A- only comes from the acid dissociation. Here, I also have HA because it's a weak acid, while in the strong acids, remember, we had no HA in the species. I have to look at 4 different equations. The ionic product of water, Kw, here it's written Ke, electroneutrality of solution, again, the pluses on one side, the negatives on the other, and this is the same as the strong. We have the same species. So this is H3O+, A-, and OH- on the other side. Conservation of matter. The concentration of the acid, now all of the acid is between two species. Either the acid is in the HA form or it's in the A- form. And so we're conserving the mass. So no matter what species it's in, all the concentration of whatever species is going to be totally equal to the total acid concentration. Dissociation constant of the acid is HA. If I take all these in together, and from the electroneutrality principle, here, if I go with A-, if I solve for A-, A- will be HA minus OH. And instead of minus OH, OH is simply Kw divided by H3O plus. Great, so I have the concentration of A- from the electroneutrality. Then I get HA from the conservation of elements. The HA will be Ca minus A-, and we have the A- this form, so we're done. Great. Now I have HA, I have A-, I substitute that into my Ka expression because look, HA now is only in terms of the initial concentration of the acid, and plus A- is only in terms of H3O+. So if I substitute both of these into my Ka expression, everything will be in terms of either H3O+ or the initial concentration. I no longer have this term, A- or HA. Expand, you get a third degree equation. Okay? Now again, we don't need this. Actually, you will get into this in a lot more detail second year, okay? I just wanted to show you this because I wanted you to understand why we make approximations. Why why can't I just solve this and get the exact H3O+ in solution? Because solving this, well, now in calculators it's become easy, but you have to plug in the Ka and plug in this part, and it's a cube root equation. No one wants to solve such a difficult equation when I can do it easier and get an approximate pH. But if I really want an exact pH, guys, I have to use this cube root. But the other pHs are approximations. So whatever we did before was an approximation. First approximation, okay, so this is the same thing. I'm not going to get into it. The first approximation that is done is we assume that water is negligible, okay? So that's the first thing. I assume this. The idea that water is negligible means that my pH of the acidic solution, HA, weak acid, has to be less than 6.5. Because if it's above this and I have an acidic solution, that means that my water will start to say, wait a minute, no, I exist. Your pH cannot be above, okay? And so as long as the weak acid has a pH less than 6.5, that means I can neglect the autoionization of water. You're going to see when we get into titration curves. In titration curves, we're actually adding a base, and we can approach, pHs of weak acids with a titration, which gets above pH 6.5. All right, so if we neglected autoionization of water, let's go back to the electroneutrality. Electroneutrality, we said, was H3O+ equals A- plus OH-. But if I neglected water, there's no more water. That means OH- is negligible, so I could remove him. That means H3O+ is always equal to A- in everything else that we do. So in everything from here on, H3O+ is equal to A-. And now we have three different possibilities for the conservation of the element C, or the concentration of the acid is equal to whatever form of HA is left over plus whatever A- has been produced. And we have three different possibilities. Either HA is greater than A-, or A- is greater than HA, or I can't, neglect neither. Okay, so either one is or the other is negligible, or I can't, neither one is negligible. First case. Okay. In the first case, if A minus is negligible relative to HA, when that is the case when we have less than 10% ionization. If the acid does not ionize, its ionization is less than 10%, we call it, okay, an acid of weak strength, okay? So this weak acid has weak strength. It doesn't ionize much, which is the majority of the weak acids, by the way. In that case, let's now look at the conservation of the elements, A. So if A minus is negligible relative to HA, that means HA is simply C. And now we go to the dissociation constant, HA, of HA, which is the Ka expression. Ka is H3O plus times A minus divided by HA, of course, according to the dissociation of the HA equation, which you all are experts on. Let's now put this together. Well, keep the upper the same. Remember, HA now is what? HA was C minus A. If I had put this here, E minus concentration of A minus. But if the concentration of A minus is what is negligible, that means that the bottom, this HA, is simply C. Great. What about the upper? Well, remember from the electroneutrality principle when I said before, in the slide before, that autoionization of water is negligible, so OH minus is gone, we always have H3O plus equals to A minus. And therefore, these two are the same, and we simply call it H3O plus. Okay. Now what do we have? I can take Ka times C, that's H3O plus squared, take the square root, so H3O plus is the square root of Ka times C. Take the minus log of both sides, and we already did this in previous slides, and you get this expression, pH equals half, pKa minus half log of C. Oh my God, you know what? I feel so sorry that I actually had to show you all this to begin with, just to come up with this expression. Because if you remember before, when we calculated this, you remember all we said was HA was C, and then we said minus X plus X plus X, and then HA would be C minus X, H3O plus would be X, A minus is X. So, according to the Ka expression, that's X squared C minus X, and now we're neglecting X. So this is the expression when A minus is negligible. So X is negligible. And remember, we derived this expression for when X is negligible. We got this, H plus, H3O plus is equal to square root KAC. I didn't really have to do all this, okay? And we did that, great. And we already said, you know, when can I do this? That's where this part heads. We said we're allowed to neglect X, okay, when concentration is greater than 100 Ka. When is this concentration greater than 100 Ka? This is the part that I need all this for. I need to know when can I neglect X. Or honestly, the English way is we assume X is negligible and then test it at the end. See, is it negligible? Is it less than 10% dissociated? In the French way, we have to, you know, do it like this. So great. Concentration C is greater than 100 Ka. If that is the case, then we can neglect this A minus. Where did we get this? Let's see. We're saying A minus is negligible relative to HA. What does that mean? A minus negligible means that its concentration is less than or equal to HA divided by 10, or 1/10 of HA. Again, that's the idea of negligibility. When is something negligible relative to another? When it's 1/10 of it. Instead of HA, use the Ka expression and convert it to something with an HA value. So A minus here would be Ka times HA divided by H3O plus. Great. Now, if you notice, HA can be canceled from both sides, and we get multiply then the H3O plus here, multiply 10 here. So H3O plus is greater than 10 Ka. If H3O plus is greater than 10 Ka, take the minus log of both sides, you get that the pH is less than pKa minus 1. And that's all I really want from this, guys, that if my pH is less than pKa minus 1, then I can use this expression. If my concentration C is greater than 100 Ka, then I can use this expression. Now, I still didn't get to this part. To get to that part, instead of pH, substitute this expression half pKa minus half log C. You did that, great. And this is pKa minus 1. Put everything to one side, the numbers on the other side, you get pKa plus log C. Kind of useless expression here, but it's fine. Or take the antilog of both sides. If you take the antilog of both sides, eventually you get that C is greater than 100 Ka. Okay. So all this, when do I neglect X? Again, when it's less than 10%. You can simply find it and see if it's less than 10%. Or you neglect it from the beginning and you say, if C is greater than 100 Ka, I can neglect X, and I simply use this expression. Now, when HA is not negligible relative to, when A minus is not negligible relative to HA, and this is an acid with moderate amount of dissociation. He dissociates more than 10%. Okay, now less than 80, less than something, but at least more than 10%. If he's dissociating more than 10%, that means I cannot neglect this X, remember? And this is our method previously. So I can no longer neglect X. And you remember that we calculated, khalas, that you do this, you get the X, which is the H3O plus, and get the pH. Or you can expand it, and we did that. Now, let's derive using this methodology, simply this expression, okay? So if HA and A minus species coexist in significant quantities, that means that the conservation of the elements of A, C is HA plus A minus, and I cannot neglect A minus, and I cannot neglect HA. And from the electroneutrality principle, A minus is equal to H3O plus, because we neglected the autoionization of water. And therefore, the dissociation constant now, due to this principle and this principle, has become, since H3O plus equals to HA, then this is simply H3O plus squared. And since HA here, go back to here, from the conservation of the elements, HA will be C minus A minus. And since A minus is H3O plus, that means we put C minus H3O plus. Oh God, okay, and then you expand all this and you get this quadratic. Actually the same bloody thing as this, which is X squared divided by C minus X. This is that, without all this, okay? Clear? Okay, now you know how we could have showed you how to get the pH. Okay, so of course the pH, you have to solve for the quadratic and get minus log of H3O plus to get the pH. And here, of course, we didn't neglect anything, so I don't have this, when do I neglect or when do I consider this? For any acid, the only thing we neglected was the autoionization of water. Okay, so water, we only had a single equation. And actually, frankly, and honestly, and truthfully, I could always use this quadratic equation to calculate the pH. And this is the most correct equation to calculate the pH when autoionization of water is neglected, or you have to go to the cube root. Again, in this course, they want you to be, use the other equations. Fine, we will. If HA is negligible now, this is the third part. If HA is negligible with respect to A minus. So this is an acid which dissociates greatly, almost where the alpha is approaching 0.99 or the percent ionization is approaching 99%, which in other words, complete. And we solved the problem actually along these lines. And then we said that in this case, the acid, if the concentration is less than 0.1 Ka, we're allowed to say that this acid acts like a strong acid and simply the pH equals minus log of C, the concentration of the acid. So again, where does this come from? This is a case of a weak acid sufficiently diluted to have a behavior, again, similar to that of a strong acid. Let's see this. The conservation of the elements A. So concentration of the acid is split between two species. But if this acid dissociates pretty much completely or greatly, that means the concentration of this acid HA at the end at equilibrium is negligible. There isn't any. Kind of like the strong acids again. The C is simply A minus. Electroneutrality, because again, we remove the water, the autoionization, that means A minus is equal to H3O plus. And so if A minus is equal to H3O plus and C is equal to A minus, that means C is equal to H3O plus. And if C is equal to H3O plus and the pH is minus log of H3O plus, that means pH. An acid that has a concentration less than 0.1 Ka acts like a strong acid. When does this acid act like a strong acid? Again, where did I get this from? It's when HA is negligible relative to A minus, that I have no more HA in solution. Okay. When is that the case? Again, that's when HA is less than A minus divided by 10. And instead of HA, what should I put? I will put, using Ka expression, that the HA will be A minus H3O plus divided by Ka. That is the conversion of HA from the Ka expression, if you put it on its own. Now, if you look at this, A minus goes with A minus and simply multiply through. This is 10 times H3O plus is less than or equal to Ka. Put the H3O plus on one side and take the minus log of both sides. You get that the pH is greater than or equal to pKa plus 1. Okay. Or that the minus log C, because the pH is minus log C, is greater than pKa plus 1, and therefore the concentration, take the antilog of it, concentration of C is less than 0.1 Ka. Honestly, I have no idea why they bothered to give all this part, because if you had used the quadratic here, you would see that this X is going to be very, very, very large. Relative to C, it's a large number. Okay, but it's never equal to C. Okay, and we still could have gotten the pH using the Ka. And I solved the problem in the homework. Okay, it was number 22, I think. And go back to it. We could have solved the pH either or, in either using the quadratic or using a strong acid behavior. Great. Done with this, and that's it for the different pH of strong acids. Now you saw where concentration is greater than 100 Ka, or when this concentration is less than 0.1 Ka, or when it's in between, where you use the quadratic equation, which comes simply from the Ka expression. You could do the same for a base, and voila. Of course, we already now know that this can be done in a much easier way. If the concentration is C, then minus X on both sides, and use the X. Instead of X, put H3O plus, you get this quadratic equation. Now from here on, in my problem sets, I can, I could show you this or that, and I may just show you this quadratic and not go through the Ka is X squared divided by C0 minus X, okay? But we already solved some problems, so you didn't have to dissociate. There's, of course, another way in your book, and that shows us when is okay, there's another completely different way of getting remember the idea of when is A minus is less than HA, or A minus is not negligible. And the way that that is done is using this alpha. Okay, remember, we can write any HA equation in terms of alpha. And this is in your book. And honestly, I wanted to go through it just because it's in your textbook. But we've done things in 3 different ways now, and I don't want you to really get confused. But still, this idea is kind of interesting. You already know that I could put an equation and put it everything in terms of alpha. That I showed you, and you're okay with that. So when you put it in terms of alpha, we also derived the Ka expression in terms of alpha, and we said that that's Ca alpha squared 1 minus alpha. And we had shown this before. Now, if an acid dissociates less than 10%, that means alpha is less than 0.1. And if alpha is less than 0.1, then it's considered negligible relative to 1. So if this is less than 0.1, it's negligible relative to 1. So we're going to do this. Let's solve for alpha first. So take this expression and solve for alpha. So this expression says if alpha is negligible, so remove alpha from the denominator, then 1 times Ka is C alpha squared. C alpha squared. And that means that alpha is the square root of Ka divided by C. Now, when did we say this is negligible? When alpha is less than 0.1 or 10 to the minus 1, or percent ionization is less than 10%. So this is less than 0.1. Solve, you get square both sides. Ka divided by Ca is less than 10 to the minus 2. And if you rearrange that, you get that the concentration of the acid has to be greater than 100 Ka, such that the percent ionization is less than 10%, or that alpha is less than 0.1. That's all you really need, guys. Either the acid concentration is greater than 100 Ka, or it's less than this. If it's greater than 100 Ka, you can ignore X, or in this case, we ignore alpha. And if it's less than 100 Ka, you can't ignore alpha. Alpha is not less than 10%. You have to keep it. Okay? Just because you see this more in textbooks, in English and in French textbooks, more than the other methodology. Okay. Now, guys, this is all you really, really need, again, for weak acids. If my concentration is greater than 100 Ka, then I use this expression. If it's not, I generally use the Ka. Okay? and the quadratic without removing a minus, or if you just substitute here for the x, H3O plus, you can expand it into your quadratic equation. This is a rare case scenario. It doesn't actually happen much. This type of dilution is very odd. Nonetheless, we saw an example of it. This is when the concentration is less than 0.1 of K. Now, again, this is in terms of minus log C values, but don't worry about that. You know, it's the expansion is greater than 100 Ka. Most of the cases, concentration is greater than 100 Ka. All right, same thing with weak base, and we already discussed this. I don't want to expand. I just want to say another thing again about the pH, the element of pH. Now we saw again, where did these guys come from? And this is not a bad idea, guys, that sometimes get the pH using this equation. If the pH is, then you have to check it. The pH has to be less than pKa minus 1. Okay. Base, the pH has to be greater than pKa plus 1. How do you memorize all these? Well, the other stuff is okay. Instead of Ka, you use Kb. That's easy to memorize. But how do I memorize something like this? Again, I memorize it by the fact that pH of acid is small, so pH less than, and then pKa minus 1, because again, pH of acids is small. For base, pH is greater than pKa plus 1, because pH of base is large, so greater than, and then pKa plus 1. Again, that's a double check, and you see that in our exam booklet. A lot of times they use these validities, the blue validities. Okay, we use mainly this yellow validity at the beginning of a equation. We could do the same for a base. I'm not going to go through it though. Okay, you could go through it again. You look at the electroneutrality principle on both sides. This is a base reacting in water. Now, this is not typical for us, where we put a base reacting with H3O plus, giving you BH plus and H3 and H2O. This is called the Ka of a base. Bit odd, not typical of what we would use, but that would be the Ka of a base. Again, it's like the opposite direction of what we're used to. I don't really like it, the way it's written. Anyhow, we'll see later, okay? So. Okay, so don't worry about all of this. Again, you already know how to do calculation of base. Again, use Kb values instead of Ka, which is more typical of base reacting with water. That's what's actually happening. You get BH and HO minus. Okay, so do it the same way we were doing it. Initial concentration minus x, x and x. This is x squared divided by c minus x, but x minus concentration. And you can transform the OL minus concentration to a base, or simply solve for x. That gives you OH, get the POH, and then get the pH. That's how we do it for a quadratic. And if it's not a quadratic, x is negligible, and you simply see that the OH minus will be the square root of Kb times C. So go back to our old methods. Full summary, make sure you know how to do all these calculations. And we are done with pH and the validities in 2 different methods. I'm not going to go through these methods again. Now, if you have any questions, make sure you ask. All this week that we're going to be open for questions, okay? Take care, and we'll see you next time.